Thank you, Sean. So this is a really good follow-up with the last presentation from Pierre. So this is also an onboard system that measures slump. Oh, sorry. Can everyone hear me? So this is also an onboard system, onboard sensor system that measures slump in real time over the delivery of the system. So what I'm going to talk about today is just one producer's experience with this over almost a decade now, and some data that's associated with that. So in line of measurements that Pierre was talking about, one an analogy I just want to make is just to the weather, right? Predicting weather is not the most easiest thing, of course. So I don't know if this is Fahrenheit or Celsius, but as a temperature, it doesn't really matter, right? But when you take a look at the industry or the weather industry here, let's see if this works. So there's been a lot of advancements, right? And how do I get this? There you go. A lot of advancements in the sensor technology for weather. And as you know, we have our slump test. I don't go back as far as the Hoover Dam, but it's kind of far enough. In the 60s, you had satellites going out there, and we had our slump test here. Weather planes, right, with radar equipped with there. And I think you guys can get the idea. Right. We have drones. We fly drones through hurricanes, right? How cool is that? Yeah. And so, you know, again, back to Pierre's talk and what we'll be talking about here, you know, it's incorporating these sensors to really give you a good idea, a much better idea, and a much more frequent idea of what's going on in your concrete truck as you move along. All right, so different from Pierre's system, which is an internal probe, we measure the hydraulic pressure used to turn that drum. All right, and in correlation to, in using that, you can come up with a correlation with the slump, very much similar to what Pierre does there. The addition that we have on the system is the ability to automatically add admixture and water. So it's tied directly to a control system that adds water and admixture based on your slump sensor. So if your slump is dropping, let's say by ½ an inch, you can pump a little bit of admixture in there to bring it back up, or water. And all of that is recorded. Right? We can record all that information, and how you add that water first, admix first, or whatever, that's all up to the producer. They have complete control of that. As you can see, there's a lot of sensors on here. There's processors on here. So there's a lot of technology that obviously has to be robust. I would definitely say concrete industry is one of the harshest places for any electronics. We found that over the last decade. But once you get something on there that works, it can be really powerful. And I do want to say these systems, these are not lab prototypes. These have been out there for quite some time. So the system that I'll be talking about today, we've put over 185 million cubic yards commercially, right? So that's about 1,000 Superdomes if you go visit that in New Orleans. The best part about this is that with each one of those deliveries, you're measuring slump, or slump temperature, revolutions, drum speed, location, all of this information every 30 seconds, every 10 seconds. Over the trucks that we have on there, that's over 1 billion data points, right? There's 1 billion data points to take a look at how that correlates to human behavior, which is really interesting. So you take all this information, and it basically gets put up into the cloud. This is the hydraulic pressure sensors and the drum sensors. You can kind of get an idea. You can see when things are, water is added, for example. You can see when the drum speed changes, etc. So we get inputs from both the batch dispatch, and then you can display this all for the ready mix producer contractor on portals, right? So that they can start to look at their operations and see how they can improve what they have there. So just as a quick example, This is it's been adopted for the HS2 project, so this is the largest infrastructure project in Europe. And basically the ask for this was that they wanted to test every single truck of concrete for slump and strength. So that takes a lot of manpower to do. Over 3 million cubic yards for this one contractor. That's what they were responsible for. And essentially, they could not hire enough people to do all of that quality control. So they were looking for a sensor system to give that to them. And so they've chosen this sensor system that we'll talk about today. And so they're able to have slump measurements, not just for every delivery, but the entire, every 30 seconds in that whole delivery. And that helps them to be accountable to the government. This just gives you an idea of accuracy for these things. So after calibration, so anything green, dark green is 95% when you compare it with an ASTM test. This is the amount of testing that they've done just to qualify this. So it's up to 16,000 slumps. And you can see the accuracy runs very high. As they get new mix designs, sometimes they try to sneak new ones in there that we don't know about. We actually have a system that automatically learns over time. So the first couple aren't going to be good, but over time it's going to get you back up to that 95%. So this is currently being used as their standard way of measuring slump. So they don't need technicians to do that anymore. All right, so as I said earlier on, one of the great things about this is that we're able to tie into adding water or admixture. So one of these nozzles is for water, the other is for admixture, and it's dependent on that slump measurement. So for example, over time, this is the slump measurement. The gray is the target, the green is the actual. So we've first added some water to bring it up to 100 millimeter slump here. After the slump starts to decrease, we say switch over to admix. It starts adding admix until it gets up to its target. By the time it gets to the site, you're on target, you're ready to pour. And again, you can do this in any order that you want. This is all up to the producer, and you can record all of this stuff. So it's simply a closed loop system, right? So not surprisingly, when you add a closed loop system, your quality control or your consistency gets a lot better, right? It's not a big surprise. This is 2 distributions here. So this is over 2 million deliveries for each one of these. The gray is without the management process, and the blue is with management. So obviously a much tighter distribution when you're controlling the system. But what's a little bit eye-opening is how not controlled the system is when you don't have that. And this is a surprise a lot of times to the producers themselves because you never had this data, right? You never measured every slump. You never had the measurement over time. So this has been really great for the producer to understand where their variability lies and then gives them a tool to help make that better. All right. So the purpose of this talk really is to say, okay, if we've improved the slump, either through control of water, better use of water, better use of admixtures, how does that relate to our strength? Okay, and as you all know, when we design our concrete, we basically are designing for a specified concrete, but obviously if your average strength was your specified, 50% of your deliveries are going to be under strength. Right? And so there's this, what's called a required compressive strength. You're basically shifting your distribution so that you only allow a certain amount of tests that are going to be under the limit. Right? Whether it's 1 out of 100 or whatever. But that's how you do it. And basically the amount of overdesign, as we would say, is dependent on how wide your distribution is. All right, so if you're really wide, you really need to design for a much higher strength to ensure that you're not failing as much. And so this just illustrates that. So again, if we're tightening up the distribution on the left, are we tightening up the distribution on the right? All right, and I'll kind of give a short way of seeing how we can look at that. All right. So before I get into that, we just saw the distribution of your strengths. All right. So what this plot basically shows is that each one of these boxes here, each one of these columns here, is a different mix design. Okay. And we basically took the histogram, and it's kind of like we're looking at it from above. So this is your average for this one. The box is 1 standard deviation, plus minus 1 standard deviation. And then the darker the boxes here, the darker the color, is the more data points that were in there. Okay? And sometimes the reason why I do that is that, so for example, you have this mix here. You have a strong concentration of data here, but the average is here. So this might point to maybe there are 2 different labs, right? Maybe there are 2 different plants. So it kind of gives you a little bit more granularity on that. Aside from the data that's in these boxes, what I have also plotted is the specified strength. So this, in this case, all of these are 4,000 PSI mixes, all right? And then through ACI, you can calculate that required strength, which is this black line here. So if you have a great mix, your average is going to be right on the line. Your over-design, your unnecessary over-design is very minimal here, okay? And again, you can see that this is a great mix because you're right on the line. You have you still don't have any failures. Even theoretically, you could. None of them are below your 4,000 specified limit, and that means you're not spending more money on extra cement. Sustainability as well. So the great thing when you're looking at this is that you can quickly tell what mixes that you might want to look at from a producer standpoint to say, hey, should we be taking cement out of some of these mixes, right? Now, it's not for all of these because some of these require early age strength, right? This is all 28 days. Some might have cement contents in the spec, so there's all kinds of those things as well. But at least you can go by and the producer can quickly spot out which ones they can take a look at. All right, so, and in this case, this producer actually selected one, had a high amount of volume, and a mix that they could take 30 pounds of cement out. So this is just a nice way to be able to do that. So now what I want to get through is to kind of take a step back. So worked with a producer, been able to look at strength since 2014, and this includes time before the system was installed. All right. And so what we've done is calculate the theoretical cement over design. All right, so it's basically, if I looked at this strength difference, or sorry, this is actually theoretical strength over design. So this one right here is, I don't know, that's about 1,000 PSI. Right, so that would show up as 1,000 PSI over here. So that's how we generate that graph. And so we're doing this year by year. And so the one thing that you can see here is this is the blue shaded area is when they turned on water management. And you can see that over time, they're starting to look at their mixes, realize the standard deviation has come down, their over design has gone up because of that, and they can start taking out cement. So this is all a certain specified strength. So this is not one mix design. But as they go through their development, they'll either make new mixes or edit the ones that they currently have, and they'll start to pull out cement for those things until it looks like it's stabilizing a little bit. All right? So this is pretty interesting. This is one single mix design example. And so you can see that translating, getting your standard deviation down on your slump in water can help them be more confident about taking some of the cement out. And again, this is one tool, as Joe said, as Pierre said, you know, I'm not going to sit here and say this is the only reason for the cement that's coming out, but it's a way for them to be comfortable or feel less risky and be able to pull some of this out. All right, so now if we go and basically take all of the mix designs, so this is one mix design, if we take all of their mix designs within a certain, like a 4,000 PSI, we'll get this plot, all right? Different colors are different mix designs, so you can see that there's just a lot of data here. What this line is basically the percent of the mixes here that were managed, right? So before they had the system, nothing was managed with water. They took about a year to start getting into this process, which is not just a flip of the switch, right? You need to change behavior. You need to get people comfortable with this. And so it took some time, and you can see that they're almost managing all of their mixes now with this water. And it's a little bit, because of all the data here, this is kind of torturing all the information, right? Pull out what you want to hear. But over time, both the spread of the data and it ends up pointing lower. And so one way to do this is let's just cut this in half. Let's just make two populations. So we'll just look at before. If there existed a time when they were measuring slump and not managing, we'll look at that, and then the full management part of that. That'll be the next couple slides. So, sorry, I just want to make sure. Okay, fine. All right, so again, no system, measure only, and then manage with water. So this is slump versus target. So I do want to say, this is all manual slumps, and these are slumps that are collected for the samples that they take strength with. Usually somebody's watching, and they're going to do a pretty good job with that. I wouldn't say it's necessarily representative of everyday behavior, but this measure only, this is from the system itself. So you can see this increased. I would say some of this is just people getting to learn the system. But also this is always going to give you a pretty true measurement here. You can see with the managed water, the slump versus target basically became half, right? So much tighter, consistency around here. And then basically we do that theoretical strength overdesign. And so you can see that starts to decrease as you move from no system to measuring. And then finally managing with water, you can start to bring that down. Just a couple more slides here. This is also, let's see, the cement content. So how much cement they could start pulling down. A nice data science trick is you don't start at zero. So there's not, so they start to pull some of the cement out for those things, and that'll continue as they get more comfortable with their system. But the other half of this is because that standard deviation was coming down, the inherent overdesign is also coming down. All right, and then the last slide here is really talks to, this is the percentage of tests that were under the spec strength. So you can see overall this producer does a pretty good job. You're aiming for 1 in 100. A lot of times you'll see producers that don't want any test results coming under low breaks. And what happens there is that you're really putting in a lot of cement so that you have 0. You are allowed 1 out of 100 for these tests, so that's kind of the target most of these people should be looking for. Of course, depends on your mix and your spec and all that kind of stuff. So you can see with the system, measuring starts to come down a little bit, but it's really with managed water in these cases that they're able to get less risks for this, right? So less risk, you're able to see, you have more visibility on your system, and then for a lot of times you feel more comfortable taking out the cement knowing that you're going to hit those strength targets because you have a constant pulse on your operations. Right. So today, this is a short presentation, but we talked about closing the loop with this management and just seeing how tidying up the variability on your water and slump side translates to your strength, and then of course you can start to pull out some of this. All right, and then with that, any questions?